All right, welcome here. We are going to look through volumes of revolutions. Now, we talked last time about disks and washers, but here's just to go through again. Finding the volumes of revolution is if we're going to take a curve and rotate it about some axis. That's going to generate a three-dimensional figure. We're going to be able to find that volume. Now, a reminder, volume, we're going to take the integral of an area section multiplied by dx. Volume is that base area times that infinite thickness that we're going to add all together. This is section 7.3 out of our textbook, so look for some examples in there. Go through, and I'm going to do my best to illustrate some extra things so that we can make sense out of all of it. Now, the first example we have, we're going to rotate y equals x about the x-axis, going from 0 to 1. So I'm going to take our square root curve, and I'm going to rotate it around the x-axis. The idea behind this is if we rotate it, we're going to have this three-dimensional figure that comes around almost like a bowl. We would call this a paraboloid. Now, what I'm thinking about is going back to the idea, I'm going to take the integral of my area dx. Now, when I rotate around, I get this shape, which is going to be a circular region. So that, finding the area of a circle with some infinitely small thickness, which is going to be dx. So I think about area of a circle. We need pi r squared. So area, we're going to have pi r squared. So what is the area of that circle? Well, the radius is going to be the distance to the height of that curve at that specific point, which we know at some given point is xy, or in this case, it's x square root of x. So the radius is the square root of x, giving us the area of a single disk, pi is the square root of x squared. Now, finding the volume, that's one specific disk. Our volume of one disk is going to be the area times dx. So the volume is going to be pi, I can simplify that, x dx for one disk. Expanding, we want every single disk that makes up our full shape. So our volume is going to be the integral based upon the bound 0 to 1. I can factor out the pi, x dx. Integrating, we've got pi, f x squared, evaluated from 0 to 1. 1, we have pi over 2. Think geometrically. We are slicing down the center of this. We've got a single circular disk that we're going to take. Hence, the disk method defining the volume of a revolution. Back to the initial curve, that disk, that's our radius. We're taking that and spinning it around. I'm going to take the same curve, do something a little bit different. Rather than rotating around the x-axis, we're going to rotate around the y-axis, from y equals 0 to y equals 1. So now, when we are rotating around the y-axis, that horizontal segment becomes our radius. That horizontal segment becomes our radius. Now, see that? Best I can do right there. If I rotate this around, all right, the section almost looks like a funnel going down. Let's focus on one of those single disks. The radius of that disk is going to be the distance from the y-axis out to our curve. I'm going to take my y equals square root of x and rewrite it in terms of x. So this would be x equals y squared. We're still going, I mentioned, from y equals 0 to 1. So there's y equals 0 to y equals 1. But our radius is now x squared. That disk, that circular cross-section, think about area of a circle, pi r squared. My radius is now defined as that x distance from the y-axis all the way over. And x is y squared. So the area is pi y squared squared. We want to think about the volume of an infinitely thin disk going around. In this case, it's dy. That will give us the volume now. And we want to integrate from y equals 0 to y equals 1. So we have the integral 0 to 1. I'm going to factor out the pi. Y squared squared. So y to the fourth dy. So we have pi 1/5 y to the fifth. Evaluated from 0 to 1, we have pi over 5 is our volume. The idea is, think about this geometrically. How can we draw a circle through there? What's our radius? And so what's the distance from some point on the curve back to the axis of rotation, be it horizontal or be it vertical? We touched upon last week what happens when we have the area between two curves rotated about something. This, if we take our area in between the curve, there we go, y equals x to y equals x squared. Now we can think about this. Y equals x over that region is the top curve. Y equals x squared is the bottom curve from 0 to 1. We're going to take this curve, spin it around the x-axis. So what that does is it's going to give us this volume of revolution. But we're going to have this outer disk that we looked, but also this inner disk that's not going to be covered. So thinking about that single value, we have what's known as a washer, thinking about a nut and a bolt. So we've got the outer value, we've got the inner value. Back to geometry, thinking about how you found like the area of those bullseye rings. Well, we could take the outer area, in this case I'm going to call the outer radius, and we subtract the area of the inner radius. So the area of one ring, outer disk, pi the outer radius squared minus pi the inner radius squared. Now here we need to think geometrically. The outer radius, that is given by our outer curve, y equals x. So the outer radius, one single disk, we've got pi x squared minus pi, our inner radius, that's given by y equals x squared. So we've got pi x squared squared. Now to neaten up, the area of one single disk is pi, we've got x squared minus x to the fourth. Now that's for one single disk. If we give it some infinite thickness there so that we've got a volume to it, that's our dx in this case because we are moving horizontally. So our volume of one single disk, we've got pi x squared minus x to the fourth dx. And if we want every single disk added together to give us the entire volume, we take our integral. Horizontally, we're going from 0 to 1, 1. So x from 0 to 1. I'm going to factor out the pi. We have x squared minus x to the fourth dx, giving us pi. We have 1/3 x cubed minus 1/5 x to the fifth, evaluated from 0 to 1. Giving us 1/3 minus 1/5. So we have pi 1/3 minus 1/5. Of course, is 5/15 minus 3/15 gives us 2 pi over 15 is our volume. What happens when it's not the x-axis? When we have some other axis of rotation. Now we could do this horizontally. Horizontally, just like the last, we'd have dy, but we'd have a washer that's horizontal. What if we have some other line? So now I'm going to take that same area, but instead of rotating about the x-axis, I'm going to rotate around the line y equals 2. So we're going to take this, spin it around the line y equals 2. What we need to think about is how that's going to look. I consider things geometrically, where all the way on this end, we're already one distance away. So if this rotates around, we're going to have this opening to our bowl. Here, we are 2 units away. So it's going to be 2 units away when we rotate around. So trying to get an idea of what this might look like. There's the cross section. We've got this bowl with this inner washer lined up there. So here's what we need to think about. Think geometrically. If we slice through this, we're going to have, again, this washer cross section. I realize that's not the best circle ever, but it is what it is. We can find the area, and therefore the volume, when we add the dx thickness to it. Well, our outer volume, our outer radius, is going to be the distance. Keep going back. Our outer radius is going to be the distance from the line to, well, in this case, it's y equals x squared. So the distance from 2 down to x squared. So my outer radius, 2 minus x squared. Because I'm at 2, and I need to subtract that distance away to figure out what I've got. My inner radius is going to be 2 minus the inner curve is x now. For inner radius. Just like before, area of a single disk, we've got pi, the outer radius squared, minus pi, the inner radius squared. So A equals, we've got pi 2 minus x squared squared minus pi 2 minus x squared. Making this volume, we multiply by dy, because this is the area of a washer. So we have, I'm going to factor out the pi, we've got 2 minus x squared squared minus 2 minus x squared dx. Gets to this volume for a single disk. Now expanding, we want the entire volume. We're going to do the integral from 0, still 0 to 1 is the intersection. Factor the pi. We can expand that. We've got 2 minus x squared squared minus 2 minus x squared dx. And you can very easily integrate that to find the volume of revolution. Essentially, think about this geometrically. If you take a slice through this, you've got this distance that you need to account for. That distance from the center to that outer piece, well, what is the value of the outer piece? It's going to be 2, subtract that value. What's the distance from 2 to the inner piece? It's going to be 2, subtract that value. Think about the washer. It's going to be the outer area, subtract the inner area. We multiply by dx or dy if we're going horizontally to turn that into volume. And then we integrate over the bounds that we have. You can take care of that. Try out the practice. See you later.